Before we begin, I should explain my outfit. I was given this lovely bear suit by my niece and nephew for Christmas, and I discovered that there just aren't that many places to wear a bear suit, and that was rather distressing. And then I thought, you know what? Nothing's normal these days. So if I want to teach my lecture, give my lecture wearing my bear suit, I can. So I am. So I'm wearing a bear suit. I'm going to take the hood off though, because it's rather hot. Okay, so we are starting section 5.1, which is equilibrium analysis for nonlinear autonomous systems. So we are keeping the fact that we're going to have autonomous systems. So that's actually different from the forced oscillators that we were just looking at. We're returning to differential equations that we can write without ever having to write the symbol t, even though everything's a function of t. Okay. But they're not going to be linear anymore. Now what that means is that we can have different types of terms. So I've got a couple examples up here. We can have things like cosine of x. We can have x and y plugged into other functions. We can have things like x times y. We can have things like x squared. Notice if I were to multiply this out, I'd have an x squared in here. So we're allowed to have different types of terms other than just x's and y's. Now, even if we had a linear differential equation, if it was not autonomous and not constant coefficient, we could have functions of t as our coefficient functions, but we weren't ever doing anything with x and y except just multiplying them by the coefficient functions. Now we can multiply them by each other, we can plug them into other functions, and all that sort of thing. So the rules are going to change. We're in particular going to be looking at equilibrium points. So two things that are very important here. When we had a linear system, we could have one equilibrium point, the origin, and the origin was always an equilibrium point. Or we could have an entire line of equilibrium solutions, so infinitely many that formed a line. Or we could have the entire plane consisted of equilibrium solutions, and that was just really boring. Everything was constant. Okay. Now, the origin is not necessarily an equilibrium solution. Okay. So you'll notice here, if I plug in 0, 0, okay, well, the derivative of 0 would be 0. That works. But the derivative of 0 would be 0, which is not 0 plus 2 times cosine of 0. So here the equilibrium solution is not an origin. The origin is not an equilibrium solution. So we can lose that. We're not guaranteed to have an equilibrium solution at the origin, but we can have equilibrium solutions elsewhere without necessarily having infinitely many of them. So I could have just an isolated point in my phase plane that's an equilibrium solution that's not part of a line of equilibrium solutions. Well, it would have to go through the origin. That's not part of a line of equilibrium solutions. So what we have with equilibrium solutions can drastically change. What I want to do is I've got two systems up on the board here. I want to just find the equilibrium solutions. Okay. So the equilibrium solutions are going to be where x prime and y prime are both 0. So of course, if x prime is 0, then I get 0 is equal to y. Plugging that in, y prime is equal to just 2 cosine of x, but that also has to equal 0. Okay. So I plugged in 0 for y because I got that from the fact that x prime had to be 0. But now y prime has to be 0, so 2 cosine x has to be 0. Now that is going to give me infinitely many solutions, because that's going to be true if x is an odd multiple of pi over 2. So I can get an odd integer if I just choose n to be any integer. This fancy z is just the set of all integers, so this just says n is an integer. If I take any integer and double it, it becomes even. Add 1, it's odd. So this gives me odd multiples of pi over 2. So I would have infinitely many equilibrium points at 2n plus 1 copies of pi over 2, comma 0. But notice, while there are infinitely many, they're not attached to each other. They're all spread out over the plane without lying in any line. Or without forming a line, rather. Okay, if I look here and I want to find my equilibrium solutions, so I know this has to be 0 and this has to be 0. I also have a third piece of information. If they're both 0, x prime and y prime are equal to each other. Sometimes I see students just use that, but x prime equaling y prime doesn't mean that they both have to be 0. So I want to make sure that I know that that's 0 and that's 0. A consequence of that I'm allowed to use is that they're equal to each other, but it's not enough to just set them equal to each other. What I'm going to do here is I'm going to first of all distribute and then factor. So 4x minus 2x squared minus xy is what I get if I distribute the 4x here. And y prime is 3x minus y squared minus 4xy. Now, from the x prime equation, I can factor out an x. So I get x times 4 minus 2x minus y. And from the y prime equation, oops, sorry, that was a 3y for that first term. So from the y prime equation, I can factor out a y, and I get times 3 minus y minus 4x. Now, both of these things have to be 0 if we're at an equilibrium point. So, I'm going to be very careful with my ands and my ors. I need x prime to equal 0 and y prime to equal 0. X prime can be 0 one of two ways. X could be 0 or 4 minus 2x minus y could equal 0. So I need one of those things to be true, and there are two ways that y prime could be 0. So I need y to equal 0 or 3 minus y minus 4x to equal 0. So let's just start trying things. So if x is equal to 0, that covers this first condition here. Now, I need the second condition satisfied. One way to do it is to make y 0. Excellent. In this case, the origin is an equilibrium solution. But I could also have x be 0, and if y isn't 0, I could have this factor be 0. Notice that factor becomes 3 minus y equaling 0, because the 4x is 0. So that would mean y is equal to 3. So that's what I get if x is 0. Now, I do have this other possibility I'm going to come back to, because I'm going to explore now what happens if y is 0, because x or y being 0 are just the simpler things. So if y is 0, that takes care of this. We've already seen that if x is 0, that's going to give us the origin, which is an equilibrium solution here. But I could have this. So that becomes 4 minus 2x equals 0. So that would mean x is equal to 2. Okay. All right. Now, the other possibility is that neither x nor y is 0, but 4 minus 2x minus y is 0, and 3 minus 4x minus y is equal to 0. Now what I did here is I lined up the x's with the y's. So I switched the order of those terms so that I could line up my x's and line up my y's. Now, I think what I'm going to do is just subtract these two equations. 4 minus 3 would give me 1. Negative 2x minus a negative 4x would give me a plus 2x. Negative y minus y gives me 0. The y's drop out. That's why I did this. I noticed that I had the same number of y's so that if I subtracted, they would drop out. And 0 minus 0 gives me 0. So if 1 plus 2x is 0, then x is going to equal negative 1/2. And now I just need to plug back into either of these equations to solve for y. So let's just take that first one. This becomes 4 minus 2 times negative 1/2 minus y equals 0. That's going to be 4 plus 1 minus y equals 0. So y is equal to 5. So we have 4 equilibrium points here for this particular system of differential equations. I should have mentioned while I had it up there, that actually corresponds to a competing species model that we could have. Okay, so we're able to find our equilibrium points. I'd like to be able to do an analysis of the equilibrium points similar to what we did with linear systems, where we will classify them. Some of them are like a sink, they draw everything towards them. Some of them are a source, and that reminds us of people we don't like. And some of them were spiral sinks or spiral sources, so they got fancy. Then we had saddles and stuff like that. It would be nice if we could also classify these things as well. Okay, so we can in many cases. What we're going to do is we're going to say, okay, the system of differential equations that I had wasn't linear. But what do we often do in math? We go into denial. We say, this isn't linear, but it would be nice if it was linear, so I can come up with a linear approximation. I mean, it's a fundamental thing in calculus. We start with the tangent line, which is a linear approximation of a curve. So that's what we're going to do. We're going to try to come up with a linear system that approximates the system of differential equations we have that is not linear, so that we can classify the corresponding equilibrium point in the linear system and hope that that information transfers back. So I think what I'm going to do is I'm going to pick this one, because this one looks the most interesting, because nothing's 0. And we'll work with that one, and we'll start that in the next video. I am going to remove the bear suit just because it's hot.